to section 15.4, heterogeneous equilibria, right? Homogeneous equilibria simply means that all the chemical species are in the same phase. A heterogeneous equilibria means that some of the chemical species are not in the same phase. Let me write that out. First, let's give her a section here. Okay, again, homogeneous equilibria, all the reactants and products are in the same phase. Right? Same phase, same state, right? So they're all gas, they're all aqueous, whatever it might be. Okay, usually gas or aqueous actually. Heterogeneous equilibrium. Whoops. The reactants products are in different phases. Or some of them. I don't want to say they are. I'll put the some. Of the reactants and products are in different phases. So a mixture of aqueous and a gas, say, or solid and aqueous, or whatever it may be, okay? So now, I know you're probably wondering, well, what difference does this make, okay? Well, what difference this makes in our equilibrium expression, solids and liquids do not show up, okay? They do not show up. Basically, long story short, the concentration turns out to be constant, right? If you want to know more, you can email me and I'll tell you, or you can look it up in your book. But basically, the concentration ends up being the same for constant for solids and liquids. So solids and liquids do not show up in the equilibrium expression, okay? Let me write that down. When a pure solid or liquid is involved in equilibrium, its concentration is not included in the equilibrium constant expression. Okay? So it's not included. It's pretty straightforward actually, right? It's not included. I'll let you write that down for a moment. Get out of the way there. And I will write several examples up here on the board. And now, although I said they're not included in the equilibrium expression, they have to be present for the reaction to take place. Okay? They have to be present for the reaction to take place. Again, I'll show you in a moment. So let's take a look at some examples here. we're gonna take a look at calcium carbonate, CaCO3 solid, goes reversibly, calcium oxide solid, plus CO2 gas, okay? So let's say we're gonna write Kc for this, okay? Solid, solid, they're not gonna appear, okay? It's not gonna appear. So we're gonna have Kc, which would be simply the concentration of CO2. Kp would simply be the partial pressure of CO2. Okay? Now, even though this is the case, if we start off with CO2, we have to have calcium oxide for this reaction to happen, okay? Or we could start off with calcium carbonate and it would just start going there. But if we just have CO2 and no calcium oxide, well, you're not gonna get any calcium carbonate, okay? I don't know if that makes sense. So this has gotta be here. You gotta have both these products, even though calcium oxide does not show up in our equilibrium expression. It still needs to be there for this reaction to proceed in that direction. Let's take a look at another example. H2O liquid, plus we're going to have carbonate again, the anion, aqueous, is going to go reversibly to form hydroxide aqueous, plus HCO3 minus aqueous, like that. Okay, is what's going to happen. Let's write the equilibrium expression for this. Notice here we have a liquid, so it will not appear in the expression, okay? So we're going to have Kc, products over reactants, raised to stoichiometric coefficients. So concentration of OH minus times concentration of HCO3, 3 minus, all divided by the concentration of H02 minus. Just like that, right? There's no Kp for this one, this is aqueous. So you can't have partial pressures. But again, note, liquid is left out, right? Solids and liquids do not appear in equilibrium expressions, right? Let's take a look at an example. I'm not going to do all these. Sample exercise 15.6 on page 623 is what I suggest you look at, okay? I'm only going to do one of these. Let's take a look at practice exercise 15.6. We'll take a look at B. Oh, I guess we'll just do both of them. We'll do A and B. All right. A, they want to write Kc for this. We're going to have chromium solid plus 3Ag plus aqueous is going to go reversibly to chromium 3 plus aqueous, sorry, plus 3 silver solid. Okay? Go ahead and write out Kc for that, okay? Write out Kc. And then we're also going to do B. We're going to have, let's see here, 3 Fe solid plus 4 H2O gas is going to go reversibly to Fe3O4, which is rust, plus 4H2 gas. And then they want you to route Kp for this one. Let's go back here. So again, solids do not appear in equilibrium. So products over reactants, we're going to have the concentration of chromium 3 plus divided by the concentration of silver plus raised to the third power. Right? What about for this one? They want Kp, right? Well, again, solids do not appear. We have gas. So again, products over reactants. We're going to end up with the concentration, not concentration, partial pressure of H2 raised to its power of 4 divided by, again, Fe3O4 is not going to appear, okay? On the reactant side, Fe is not going to appear, and we're going to have H2O. Partial pressure of H2O raised to its stoichiometric coefficient of 4. Okay? Again, hopefully that's pretty straightforward. Solids and liquids do not appear in heterogeneous equilibrium. Long story short. Okay? Let's take a look at one more sample exercise. Well, we're going to just go on to section 15.5. In this section, it's calculating equilibrium constants. Yeah, I told you just plug the numbers in, but we're going to do an example here again. Okay, calculating equilibrium constants. Sometimes this is straightforward, and then obviously it can be more difficult. We'll take a look at the easy version first, where you just plug the values in. Let's take a look at sample exercise 15.8 on page 625. So I'm going to write out the equation first. We're going to have N2 gas plus 3H2 gas is going to go reversibly to 2 NH3 gas. All right? Now, so our book says after a mixture of hydrogen and nitrogen gases in a reaction vessel is allowed to attain equilibrium at 472 degrees Celsius, it is found to contain 7.38 atmospheres of H2, 2.46 atmospheres of N2, and 0.166 atmospheres of NH3. From these data, calculate the equilibrium constant Kp for the reaction. So it tells us partial pressure of H2, 7.38 atmospheres. Partial pressure of H2 equals da-da-da-da. Oh, why did they do that? Nope, that was me messing up. Sorry, H2 is 7.38 atmospheres. N2 is 2.46 atmospheres. And partial pressure of NH3 is 0.166 atmospheres. Okay? So all we have to do is write out Kp and stick the numbers in. That's it. Kp, again, products over reactants. Partial pressure of NH3 raised to its stoichiometric coefficient, which is 2. Partial pressure of N2 raised to its stoichiometric coefficient, which is 1, and then the partial pressure of H2 raised to its stoichiometric coefficient, which is 3. Right? Let's plug in our numbers. So partial pressure of NH3 is 0.166 atmospheres squared, right? Partial pressure of N2 is 2.46 atmospheres. And then the partial pressure of H2, 7.38 atmospheres raised to the third power. Okay? Make sure you get your order of operations all correctly entered in there, right? Making sure you square and you cube and whatnot. And according to our book, sorry, where am I at? We get 2.79 times 10 to the minus 5. Okay, 2.79 times 10 to the minus 5. So what is that telling us? It's telling us that the equilibrium lies with the reactants, right? Again, it's less than 1. And we can actually see that. Partial pressure, this is 0.166, 2.46, 7.38. So the equilibrium lies on the reactant side. Okay? Well, again, pretty straightforward, I hope. Not too much trouble. I'm going to end there for today, and we'll be back with another lecture on Monday. Have a nice weekend.